Hi everyone and welcome back. We're going to take a look at another example of nodal analysis. We've already done one example, fairly simple and straightforward. This one's a little more complex. First thing is we need to identify essential nodes. And we have one essential node at the top where we have currents coming in and currents coming out. So we need to identify essential nodes. That's our first step. Then once we do that, we need to identify the reference node. The reference node is assigned by us, and that will be our ground point, if you will, or 0 volts. So there is what we are going to choose for a reference node. Hopefully that seems like a good choice. Hopefully that makes sense why we want to put it there. Then once we have that, then we can identify some of the other nodes. Maybe they're not essential nodes, but we should look at that and figure out where the current's flowing. Hopefully you can see that since we have a DC voltage source near the bottom, it is going to push current upwards. The current source on the right is going to push current up. So we have current flowing into that node, so it must exit the node somewhere. So the current is going to exit through R1 and go to the left. We're going to label these with A, B, and C so we can talk about each one of these nodes and just figure out how we're going to write some expressions for the currents. So we'll just label our diagram here and then we'll take a look at it from there and see. Now, we do have a voltage source below the load, so it is a little bit different. Identify the direction of the currents. Hopefully that makes logical sense. Typically what happens is if you do this correctly and you check at the end, you'll see that you were either right or wrong when you're making assumptions about current flow. So we're making those assumptions. They seem logical. Hopefully it does to you. Now, we do have the voltage source below the load. So I think what we'll do is we'll put in just another node point just to maybe make it clear what we're doing. So we'll make that node D right there. And maybe that'll help you understand what's happening as we write these expressions. So over on the right hand side, we have 4 amps from the current source. If we take a look at the load, we have VD subtract VB divided by the load resistance is going to give us the current going up through the load resistor. Over on the left-hand side, the bigger voltage is voltage B. We can make that assumption, subtract voltage A, and then we can divide by R1. So there's the expressions we have for each one of the currents. And then what we're going to do next is put that all together in the form of an equation using KCL. We need to note what currents are going into the node and what currents are exiting the node. So we have VB minus 0 because really VA is the ground point when you look at it. So we can put that as VB over 2. That's the current exiting. That's equal to the current entering the node, which if we just write out these expressions that we have above, then that's going to give us our equation. So I'm just getting those values from there. And the current source is supplying 4 amps. So there's our equation. We are going to solve that equation. Now, if we just take that equation and move it to the next step here, this is what we have. Now you might notice something about VD. VD is at the top of the voltage source, if you will, which is really 60 volts. So we actually know what VD is. We don't know what VB is, so we're going to keep it as VB. But like we said, VD is 60 volts from the voltage source. So we can plug in that, subtract VB, which we don't know, divided by 8. And we can add the 4 on the end. And there, we have a rational equation with one variable, which we can solve. We just have to be careful with the denominators here. If you want to, from this point here, just put brackets around both sides and multiply by 8. As long as you're careful, that should work. So on the left, we have 4VB. That's equal to 60 minus VB. And that 8 has to multiply by the 4 as well, so that's going to be plus 32. Solving for VB, we just need to add VB to both sides. We'll get 5 VB equals 92. Solve for VB. And that is 18.4 volts. So now we can determine the load voltage and the load current. We now know the voltages at all the nodes. Remember, VD is 60 volts. So if we want to find the load voltage, we're actually going to have to take 60, which is VD, subtract VB, that would be the drop across the load. Divide that by the resistance of the load, and that would give us the current. But if we just want to find the voltage across the load, it's just 60 minus 18.4. And that gives us 41.6 volts. So there, we know the load voltage. So that's the drop across. It's a drop of 41.6 volts as we go upward, if you will. The load current, we just need to take that load voltage and divide by the load. So 41.6 volts over the load, which is 8 ohms. And that gives us the load current. Which is 5.2 amps. So there, that is using nodal analysis. We need to find the voltages at the nodes. That will help us determine all the currents. And we can actually check the currents and see that they actually work. We have 5 amps, 5.2 amps going up. We have 4 amps going into the node. And if you do the math, you can see that we have 9.2 amps exiting that node. You can draw that diagram out just to check. 5.2 going in, we have 4 going in, and coming out is 9.2 amps. That's it for this example. Please practice these and see me in class if you have any questions. That's it, and we'll talk to you soon.